Hello and welcome to Lesson 5 of Python for Musicians, a Python tutorial series aimed at musicians of all levels. We'll be taking a short break from synthesis today to look at classes and object-oriented programming in general. This will elevate our capacity to make complex projects more manageable and allow us to move from creating one-shot samples, as we have been doing so far, to create live and interactive projects that can do all kinds of things. The plan for the day is to briefly talk about the object-oriented programming paradigm, how it's useful for us as musicians and creative coders, and then we'll jump into Python and define a class. We'll define the basics of an audio processor class that can act both as a synthesis engine and as a processing engine. We'll give this audio processor class some methods and an initializer and explain why and how these are useful. So what is the object-oriented programming paradigm? It's a way of thinking about programming, specifically code structure, in terms of objects. We instantiate objects from class definitions that we define. This allows us to write code whose functionality we can use over and over while having our code readable. This wouldn't be any classes and object-oriented programming lesson without the classic plot twist that we've already used classes. The nice people who created NumPy defined a class called an ND array, instances of which we have been using over and over. It's what allowed sign functions to operate on a whole list of numbers at once, while still being readable. It's what allows us to get the size and the shape of an array by using array.size and array.shape. This lesson is about defining custom classes or custom data types that have certain properties and methods that are useful to us. So the big question is, how can classes be useful to us? The first point is that we define the classes, and that makes us in full control of what things can and cannot do. Ideally, we want to keep our classes simple. If they do too much, they can get overused and end up destroying the flow of our code. They need to do one thing, but do it really well. Examples of classes could be synth blocks, like oscillators and envelopes. We can define audio processors, delays, reverbs, filters, maybe managers like timekeepers, arpeggiators, sequencers, and information classes like music notes, scales, chords, and anything else we'd need for our project. Ultimately, object-oriented programming is about division of labor, where every class of objects has its role well defined. As a programmer, you need to orchestrate your code elements like a dictating economist. Who does what they need to do their job, and eventually, how can I make them work faster and more efficiently? We're about to jump into Python to code our audio processor class. If this is your first time encountering classes, I encourage you to follow along with me, typing out the code as we go, to build up a habit of coding these things. As usual, I've documented the whole lesson into a GitHub repository, which you can find in the description for you to refer to later on. So before we can use classes in Python, we need to define the class. In Python, that's done by typing out class and then the name of your class that you want to define. You finish that definition with a colon at the end, and then if you have nothing else here, this is now a valid class, but it has absolutely nothing inside, so there is no point to this. So let's add some variables in here. Let's say that an audio processor is going to need to know the sample rate. So let's give it a sample rate of 44,100 Hertz, and let's give it a block size of 256. So what this means now is that a sample rate and the block size are class properties to any audio processor instance that we then define. So if I came here into the main loop of our function and I said that we're going to define a variable called processor, and it's going to be an audio processor, if I came here and called processor.sampleRate, this is now going to return 44,100. So if I were to print that, and we run this command now, so Python class intro, it's going to return us 44,100. And that's because this processor here has an inherent property that its sample rate is 44,100. Now we can, of course, change the value of this sample rate from outside the class. So if I wrote processor, which is our variable here, dot sample rate, and we assign it a new value of 48,000, and then we printed this command over here, we should now get 48,000 instead. So on its own, this doesn't do so much. This is an audio processor class, and it needs to process audio in a streaming fashion. And when I say a streaming fashion, I mean it needs to process a large stream of audio. It could be infinite, it could be a really large file, but it needs to do it in chunks, and that's what this block size here is. So block size is saying that it needs to process 256 samples at once. Now at this point, every time we create a new audio processor class, they're going to have a sample rate of 44,100 and a block size of 256 by default. And this is not something we can change unless we ran this command. But say, for example, we know from the start that our project sample rate is 48,000 or is 96,000, then we can make our code adapt to this. The way we do that is by introducing an initializer. This is a method to the class that runs on initialization. The way we would do that is we write define, and this is a double underscore method. So we write double underscore init double underscore, and then we open and close the parentheses, and we put that colon at the end. Now every method to a class needs to take a self parameter, and I'll explain in a little bit what that is. But for now, write self, and then any parameter that you want the audio processor to take in upon initialization. So some of the important parameters exactly here would be sample rate and block size. So let's type those in. So sample rate, which is an int, and block size, which is also an integer. So if we said here that the sample rate of our audio processor is going to be equal to the sample rate passed in the function, and same here with the block size, this doesn't say much because these variables are stuck within the function. So to get them out of the function, you need to write self before. So self dot sample rate and self dot block size. And this is why the self here comes in. So self is basically the instance of the class. So now for this code to make any sense, our audio processor here needs to take in two variables. It needs to take in a sample rate and a block size. We are going to give it a sample rate of 44,100 and a block size of 256. And so now if we were to print the sample rate of our processor, we should get 44,100. Now, because this is an audio processor class, it needs to process a buffer that is given to it. So in our main loop, let's create a buffer of audio that we're going to call input buffer. And for now, it's just going to be one chunk of zeros. So it's going to take in the block size, so 256, and it's going to be a mono channel, so it's 256 by 1. In the main loop, let's create two variables here. So let's create a sample rate variable of 44,100 and a block size of 256 so that we can actually use these in our code. This is much cleaner. So this is our input buffer, and we want to give this into our audio processor. So our audio processor needs to have a method that says ProcessBlock, and that will change our buffer here that we give it. So let's do that. Let's create a new method inside our audio processor, and we're going to call this ProcessBlock. And it needs to take in the self so that it can understand what parameters the audio processor has. Otherwise, we wouldn't have access to sample rate and block size in this case. And it's also going to need to take in a input buffer. This input buffer is going to be a NumPy array. So now it's time to define what is going to happen to this array. So for the sake of example, let's say that it's going to take in the in buffer and it's going to add to every sample in that in buffer 1. So remember, the in buffer here is all zeros. So if we run our command now, so we say processor.processBlock and we give it our input buffer, and then we were to print some values in here, let's say up to 5 of our samples. Let's run this and see what happens. It's given us all ones now. So what we've done now is we've taken this 0, we've ran it through the processor, and the processor added 1 to every single sample in our buffer. Now let's make this audio processor a bit more musical. We haven't looked at synthesis in this kind of framework yet, so let's, instead of doing synthesis or any effects processing, let's instead read in a WAV file into the audio processor, and then every time we call ProcessBlock, we're going to be adding a new chunk of the audio that's stored inside the audio processor inside our new buffers. So for that, let's create a new method in the audio processor, and we're going to call this one load audio. It needs to take in the self, and it needs to take in a file name, which in this case is a string. We'll be using Librosa to import our audio files. So we need to import Librosa at the top of the file, and then in our load audio function, we are going to call self.audiodata. So this is going to be the variable inside our audio processor that's going to hold this audio data, and we're going to run librosa.load, and then Librosa expects the file name. It also expects a sample rate that we can give it. We don't have to. By default, it takes in a sample rate of 22,050, but because we have a sample rate here and we want to use it for future reference, we can give it in here. So we write self.sampleRate, and because this returns a tuple with a sample rate, we don't really need the sample rate because we've just given it here. So let's take in only the first element that this provides, and this will return a mono file. So we need to reshape this to have a block size and an extra dimension here, even though it's just 1. And the way in Python to do that, especially with NumPy, is to say that we want the entire array, and then we can give a comma and then np.newAxis. This will basically create a new axis to this audio data. Let's give a statement here, loaded audio file successfully. So before we process our block here, let's run processor.load audio, and let's load in a file that we generated in the last lesson called chord.wav. So if I run this now, it should tell us that it has loaded in the audio file successfully, and it still did the old processing on the zeros. Now let's write our process block. So in an ideal world, this is what our process block would look like. It would take in everything inside the in buffer that it's received, and it will add onto it a portion of the audio data that we want to give it. So that portion of the audio data needs to have a start point and an end point. So let's give this a start index, and we'll keep it going until the end index. So let's now define what this start index and end index actually are. So the start index needs to be, well, at the first block that it's going to generate, it needs to be equal to 0. And the end index needs to be 256. That's because it's 256, or the block size after the initial index. So if on the first block it needs to be 0 and it needs to go till 256, the next block is going to take in from 256 until the block after that. And so the way we can keep track of where in the audio file we are is that once we have loaded in our audio data, we can create a new variable inside our processor, and we can call this block index. And at the start, it's going to be 0. So the starting index here is going to be our self.block index times self.block size. And just to make sure that this is an integer, let's wrap it inside an int. And as we said, the end index needs to basically be the starting index plus the block size. Now, block index at this stage is going to stay 0. So every time we run the process block, we need to increment block index by 1. So let's do that. Let's say that at the end of our process block function, self.block index is going to be 1 more than whatever it was before. Now, before we can call this process block completely finished, there are 2 more things that we need to address. The first thing that we need to address is that audio data is a 2-dimensional array. So we need to make sure that we give it the second dimension here, and we want to take in everything inside the second dimension. And the next thing that we need to address is that when we reach the end of the audio file, end index over here is most likely going to be out of bounds, because what are the chances that the audio data that we've loaded in has a sample count exactly a multiple of the block size? So in that rare case, we need to change what portion of the in buffer is actually being affected. So one of the simplest ways to do this is to wrap this function in a try except. So now it's going to try and run this code, and if it runs into an error, it's not going to crash our Python code or anything like that. Instead, it's going to execute whatever is in this except function here. So let's create a new index here, and we're going to call this last block size. And this is going to be equal to the shape of our audio data after the start index. So check that this makes sense. So the audio data that we have, assuming we take it from the start index all the way at the end, remember this is for the last block, so it's going to be shorter than 256, or our block size. And we want to take that number. So what the shape, how long is this buffer? That's what this last block size is. And so what we need to do then is that our in buffer, we can't just change everything in there because we don't have enough samples. So we're going to change up until the last block size, and we're going to add onto that self.audiodata whatever we have left. So start index up until the end, and then the new dimension of data. So let's test this. We should hopefully not see here ones anymore, and this makes much more sense. So we have now values that are between -1 and 1. So I thought I would give a quick recap of what is important here. So there are 2 things that we looked at in this video. The first is the concept of a class, and the second is the concept of an audio processor. So for a class, this here is a class definition. And so much like a function definition, it doesn't do anything on its own. For any of this code to be executed, it needs to be run in a main function. So we created here a class called AudioProcessor, and we created here an instance of an AudioProcessor class. What we created here is an init function. It's known as a dunder method, so these double underscores here. This is because it's a method that deals with the Pythonic syntax, and there are many examples of these. It's also important to know that this processor over here is an instance of the audio processor class, and what that essentially means is that if we had another processor, it would have nothing to do with the first processor that we created. In the same way that if we had one array that's all zeros and we made a new array that's all ones, those arrays don't necessarily have anything in common, and if you change one, you're not changing the other. Now, audio processors themselves, the core part is this process block. Some people will argue that you don't need a whole class to be the audio processor. And that's probably true if you just need the ProcessBlock function here. You don't really need the whole class. But it does become really handy to have it in a class when we try to do the streaming part. And we're going to see that in the next video when we start to make sound come out of our computer as it's being executed. This will be extremely useful. But the core part is this process block here. And the idea behind it is that it takes in a buffer, but it doesn't return a new buffer. Instead, it's modifying the contents of that buffer. Which is why here, when we passed in the buffer, we didn't return a new buffer. We didn't say output buffer equals. Instead of calling this input buffer, we could have called it buffer. And that's why here, when we print the input buffer, we're actually printing what happened after the processing. When I recorded most of the video that you already watched, I actually continued for another hour or so, showing how we can transform this audio processor class and use it creatively to create like a granular effect on audio wave files. And if that is something that you're interested in, I am going to put in that code in the GitHub repository, which you can find in the description. I hope that this series is useful to you. If you have any friends or you know anyone who would benefit from this series, then do share it with them. If you would like to leave a like and subscribe, that is entirely up to you. I will see you in the next one.